And you're back. So let's talk some more about the addition rule and complements. Actually, we're going to talk about contingency tables first. Here we go. First, some vocabulary. Here is a contingency table. It is composed of various cells. Okay, each one of these little boxes containing a number would be called a cell. We have column variables, which go down the column. In other words, here are all the numbers for all the females. And then we have row variables, which go across the rows. So, for instance, the cell that is outlined in blue indicates the number of males who are unemployed. Over here at 2,509, that is the number of females who were employed. Where? Well, in the civilian labor force in 2007, who were ages 16 through 19. So, working teens. And this is published by the U.S. Bureau of Labor Statistics. So, apparently this is in the United States. Okay, so there is your vocabulary that you need. Let's go down here because as you see, I'm adding a column and a row. And I have that sigma symbol, which, what do we say that means? Yep, that means a sum. So in all of these extra boxes, we're going to put some sums. So first, let's do the sums across the table. So we're going to add up the number of males employed, and we're going to add to that the number of females employed and put the answer here. 4,837. Next, the total number of unemployed, 898, plus 654 gives us 1,552. And finally, those not seeking employment, we get 10,653. We added across the rows. Now let's add down the columns. 8,642. 2,509, etc., will give us 8,400. And if I have done this correctly, I don't have you to work with me today. If we now add across this final row, I'm getting 17,042. And to check, this column vertically should also equal that sum. And it does, yay. So we've set it up correctly. Now what can we do with it? All right, so whether we are adding across the bottom here or down the columns, 17,042 people. This is the total number we have within the table, the shaded area. If this is the total number of people, the percentage of people who were male, okay, and employed was 2,328. What percentage of the population that was surveyed here was that? Well, if you divide it by the total number of people, 17,042, you will get the percentage of people surveyed who were male and employed. That's also the probability of you randomly choosing an unemployed male from this pool of 17,042 people. Likewise, if you want to know what the percentage of people who were female and employed, you would take that number and divide by the total number of people. And you could do that for any of these numbers. If you want to know not male employed or just female employed, if you add those up, you will get the percentage of employed people versus the unemployed or not seeking employment. And that would also give you the probability, if you randomly chose someone from these 17,042 people, that you would find someone who was employed. We can do that for all of those numbers on the table, and I have done that right down here and converted them to decimal form. And as you see, not only do these percentages line up going from left to right, These are decimal expressions of percentages. You could rewrite them as true percentages like that. But if you go across, they add up. If you go down, they add up to the final value here. And if you add across, you get 1. Also, if you add down, you wind up at 1. It's a contingency table. It's going to have those properties, although the numbers inside will vary. But we can do even more with this contingency table. What is the probability that a female, okay, so I've already isolated part of the table. What is the probability that a female is unemployed? Okay, probability that a female is unemployed. So we have to look at just the females. So the total number of females is 8,400. And the number of females who are unemployed is 654. And that probability in decimal form is 0.0778, and it rounds to a 6. The probability that a female is unemployed is 7.79%. Or usually we only go to the tenths with percent. Okay? All of those answers are equivalent. I kind of prefer this one, unless I want a little more detail, and then I go with that one. Just because probabilities we're used to expressing in percentages. So the probability out of these people, if you randomly select one, not all of those people, just the female people. If you look at all the female people in this survey, the probability of choosing one that is unemployed is 7.8%. Okay, those not seeking employment. What is the probability of not seeking? The probability that someone not seeking is male. So out of all those who are not seeking, that's our reference value, the ones who are not seeking employment. And we want to know about the males who are not seeking employment. So that's 5,416. And that gives us 0.508. So 50.8%. Okay, let's go back to flipping a coin. Let's say you have two events, E and F, that are independent if the probability of E does not affect the probability of F. So our first event that we're looking at is that we flip a coin and it flips heads on the first toss. F is the probability that it flips heads on the second toss. Not on the first toss. We're not comparing heads versus tails on the same toss. Okay, that wouldn't be independent, because if it's heads, it's not going to be tails on that same flip. But these are on separate flips of the coin, separate tosses of the coin. So on the first one, what's the probability that it's heads on the first toss? What do you think it is? Sure, it's 1/2. And then, what's the probability of heads on the second toss? Let's put these up here. Okay. We could draw a diagram, right? There's the first toss, heads and tails. We flipped heads first. For the second coin, we could have heads or tails. If we flip tails first, our next flip could still be heads, or it could be tails again. They're completely independent. If we follow this tree diagram, we're going to get heads and heads. We're going to get heads and tails. We're going to get tails and heads. And we're going to get tails and tails. There are 1, 2, 3, 4 possible outcomes. How many of them are heads, heads? Well, the answer to that is 1/4, 1 out of 4. How do we get there? I started to write it out for you, and then I stopped. But the way we got there is this. Those are completely independent tosses. One does not predict the other at all. So we multiply, okay? 1 times 1 is 1, 2 times 2 is 4, and we're done. The probability of flipping a head on a coin, then flipping it again, and getting a head, is 1/4. Okay, so here is a summary of all of the probability rules. Please pause the video for a moment, look over them. Okay, here we are with our 12 numbers again. We're revisiting that too, yes. Okay, and we have A, B, C, D, F, and G labeled again. Identified, defined. Okay, so find the probability of A and B. All right, the probability of A and B. Well, the probability of A is 1/2. Okay, and the probability of B, finding an odd number, is 1/2. So the probability that you draw a number and it is both A and B, both odd and even, is actually 0. Okay, so that was these two that we were doing. Now we want to look at the probability of finding C and D occurring together. Okay, will you ever have a case where you have a number drawn from those 12 that is both less than 3 and greater than 10? No, you will not. All right, so let's look at another one. Erase those. Okay. For another one, find the probability of A or B. Now that's something completely different. It could be the probability of A. All of those are possible. The probability of B. All of those are possible. And those are disjoint events. There is no number that is both A and B. We already said that. It's right there. And let's finish writing out the full rule. We have to subtract from those the probability of A and B. We already said that was 0. Okay, so we have 1/2 plus 1/2 plus 0 equals 1. It is certain that out of those 12 numbers, if you pull one randomly, you will get either an even or an odd. So here is the rules written out symbolically for finding the probability of C or D. And the probability of C, we said, was 2 out of 12 or 1 out of 6. The probability of D was 2 out of 12 or 1 out of 6. And the probability C and D, that you will draw a number and it is less than 3 and at the same time is greater than 10, is 0. And finally, if we find F and G, the probability of F and G. Well, F is a multiple of 3 found in there. I'm going to mark it up at the top. There are the multiples of 3. 3, 6, 9, and 12. And is a multiple of 4. Okay, better do a different color up here. 4, 8, 12. Okay? So the only number up there that is both a multiple of 3 and a multiple of 4 is the number 12. So that's 1 out of 12 for a probability that it is both. So if we go about finding the probability of F or G, let's see, the probability of F, that's a multiple of 3, that's 4 over 12 or 1/3, plus 1/4, the probability of finding a multiple of 4, minus the probability of both, which is 1/12. And that means we have to convert to a common denominator. So 4/12 plus 3/12 minus 1/12 equals 6/12 equals 1/2. And finally, let's find the probability that the number is either even or it's a one-digit number. So the probability that it is even would be 1/2. Half the numbers are even. And the probability that it's a one-digit number, well, there are 9 of those, 1 through 9, then 10, 11, and 12 are two-digit numbers in our sample space. And then we have to subtract everything that is even and is one digit. So that's 2, 4, 6, 8. That's 4 of them. So we have 10 twelfths minus 4/12 is 6/12, or look at that, it's a half again.